Lab 2, Drag. The purpose of this lab was to demonstrate how multiple forces work together and give us net force, which can take a constant velocity and make it non-constant, such as drag and the Earth's gravitational force do in this case. Multiple physics principles were at play in this lab, with the most prominent being F net equals Fg plus F drag, which allows us to see how multiple forces can change motion. In short, we found drag to be a contributing factor in why we did not see uniform motion, and both GlowScript and our tracker model concluded that drag decreased the rate of acceleration in the negative y direction. The main idea we observed was that when there are two forces acting on an object that are not equal and opposite, the net force is changed, and in turn acceleration is changed. Although gravity was causing our paper ball to accelerate at negative 9.8 meters per second squared at first, the force of drag caused the ball to accelerate at a decreasing rate. If we had let the ball fall long enough, the net force would eventually equal zero, as our ball would hit terminal velocity, where the force of gravity and drag are equal and opposite. The reason we chose to look at F net is because it takes into account all forces acting on an object, unlike what we did with our last lab, where we did not include other forces such as drag, friction, etc. In our experiment, the system was comprised of a crumpled paper ball, and the surroundings included everything else acting on the ball, more specifically the Earth and its gravitational force, and the air and its drag force acting against the ball. The initial conditions of the experiment show the ball moving across an arc with velocity applied to it by lightly tossing it. We chose to start both the tracking and the code at precisely the point where the ball leaves the hand of the person throwing it. In our experiment, we lightly tossed a crumpled paper ball across an arc and recorded it to later track using Tracker. We also made a model of our experiment in GlowScript to compare the two against each other and observe any differences we found. Our code again was relatively simple with the starter code, only requiring us to input a few variables to get the model going, with some additional tweaking needed to perfect it. The coefficient of drag was particularly difficult, requiring us to guess and check until our graphs matched up for the most part. The main variables we used included the force of gravity, the coefficient of drag, the delta t, the mass, the initial velocity, and the position vector. Predictions versus reality. While our data was not exact, there was a definite correlation between what we saw in our code and what we observed in actuality. I would say that they matched up for the most part and helped us to visualize what happens in the real world, furthering our understanding of what physics is and how it plays a role in every aspect of our lives. Greatest source of error yet again was due to our use of Tracker. This time we had a major issue precisely calculating the paper ball's position, which inevitably skewed our data. I found this experiment to be much more insightful than the previous one, as with more variables in our code, we were able to get our tracker data aligned much better with our GlowScript, proving that the physics principles we observe on a day-to-day basis mirror the equations we use in class every week. We could, of course, always improve our process, but for the resources we had available in the lab setting, I would confidently call it a success. What if our object was thrown straight up? The only change in velocity we would see would be along the x-axis, but our y-axis would still show the same rate of change of velocity due to drag. Our object would also hit the ground at the exact same time as if it were thrown with the same positive y velocity, but also with some x velocity. It would be interesting to see if we could replicate this in real life, as it would require a great deal of precision. Can we calculate terminal velocity from our experiment? While terminal velocity would occur at some point with any object, in our experiment, we did not have a large enough data set to accurately predict what that velocity would be. If we wanted to determine what its terminal velocity would be, there are a few ways we could accomplish this. First, we could let the code run longer by increasing the y value of the ball's initial position, allowing us to see when F net acting on the ball is zero. We could also let our object fall from a much higher location in real life and do the math to figure out at what point it stops accelerating. Overall, I believe our experiment was a success, as both the code and the tracker data lined up very well, and I think that we could improve upon it in some ways, but in general, the physics principles at play were easily discernible and made easier to understand. It would be interesting to revisit the experiment later on in the semester to see if we could further refine it using more complex physics principles as we learn them.